Now for the third exercise, if you look into the original sheet, this is just my solution file, you will see there are 3 sub items, 1, 2, 3. And interesting is several things. Firstly, this matrix has already been used in exercise 3.1, 3.1, number 2. If you remember, otherwise you should look it up. And actually, it was an example for a linear system of linear equations with one built-in parameter a. That was interesting. We had 2 special cases there, and we had to be very careful not to overlook one of these special cases. And now it turns out, had we known at that time how to calculate the determinant, which we didn't know officially at that time. So, but had we calculated the determinant and just looked up all the values of a where the determinant gets 0, we would at once have had all the special cases we have to take care of. So that's a good idea when solving a system of linear equations with a built-in or even 2 built-in parameters. First of all, calculate the determinant, and then you will suddenly find all the special cases. That's just a recommendation. Now, this matrix, this is what we do now. We want to know about the determinant. We want to calculate it, but in 3 different ways. Let's start with the official and general method, which is called Laplace expansion. I think you know it, not really. Did Martin use this expression? Probably not, but you know what I mean. So you can expand such a matrix in order to calculate the determinant along any row or any column. That's the first important thing. And now, if you have the free choice, I would always recommend take the simplest row or column. So the first column would be okay, for example. I would not, well, it doesn't matter anyway, but anyway, the first row is the simplest. So let's just use this one, okay? So now, how does it go? The determinant of A equals, now comes the expansion method. You know this sign scheme? This is interesting. It's like it always starts with a plus sign in the left upper left corner, and then the sign changes every time you change column or change rows. So every time you move 1 step to the side or 1 step up down, the sign changes. This is like a chessboard sign schema. That's nice to remember. So it starts the following. You just mark your element, your first element in the first row, in this case, expanding along this row. I start here. Then you use this number, put it there, 1, but also now you delete the corresponding row and the corresponding column. And the remaining smaller matrix, this is called a minor. This remaining matrix is now taken, better speaking, its determinant is now calculated. So you see, if this is a very large matrix, 5 by 5 or something, you would have to use this procedure recursively, but in the end, it would lead you to 2 times 2 matrices where you can easily use the product and you know, the diagonal minus second diagonal product method. Or you could even go one step further, and then if you had only a 1-1 matrix remaining, you could say this is the determinant of this is just the number itself. So that's the determination of this whole method actually. Okay, nice. Now we do it, and you see what remains is 2a2. I put this here, and then I take the determinant of this one. Next step, of course, is then to proceed to the next element, but please always remember to consider this sign table. So now we have a minus sign. This is here, the minus, but always take the element as a factor, factor of 1, and then we cross out or delete this column. And still the first row, of course. And now you see this is also clear. The remaining 4 numbers must, of course, be concatenated or put into a quadratic, simple 2 by 2 matrix. I mean, that's easy. 1a, 2, 2, and then so on. The third step, I put this away now, is then again a plus sign with factor 1, and then crossing 1, 2, 2a is what remaining. So let's go on here using product minus second diagonal product minus second diagonal product. So it's 2 times 2 minus a times a, well-known method. Okay, so 4 minus a squared. That's it. Minus, please regard the minus sign, and don't forget to to use it here also. Well, 2 minus 2 times a. Inside the parentheses, resolving them later. Also plus, what do we have? 1 times a minus 4. So that's it. If we resolve these and remove these parentheses, look carefully. What you get is minus a squared. That's the only quadratic term. Then we have minus 2a, which is plus 2a, and then also again plus a. So it results to 3a plus 3a, and then all the constants together. 4 minus 2 is 2, minus 4 is negative 2. That's our polynomial now in A. And okay, actually, it's a good idea to put this in the form of, it's not required, but it's, oh yes, it is, because now we are asked for which values does the determinant get 0. So it makes sense to put this into the form of linear factors. You know what I mean? And also I would recommend to put this minus sign aside so that we have a normalized polynomial with a leading coefficient of 1. You know what I mean? So in parentheses remains a squared minus 3a plus 2. Now that's nice because you know my very loved theorem of Vieta's theorem, which says you are looking for whole numbers so that their product is this constant and their negative sum is this one. So it's easy to guess. In this case, it's 1 and 2. These are the two zeros of this polynomial. It means the linear, the factorialization form is minus outside, and then a minus 1 times a minus 2. Now, this gets 0, of course, in two cases, either if a equals 1 or a equals 2. You should remember, or just look back and compare in exercise 3.1.2. These were exactly the two special cases where we had to be careful when solving this system. And also, of course, these were the two cases where there was no unique solution. In one of these cases, we had a contradiction, and which means we had no solution after all. And in the other case, we had, well, as far as I remember, we had a one-fold, let's say, yes, a simple manifold, like a solution line with one solution parameter. I think that's what we had. If you wonder why we don't see this here, it's easy, because the appearance of a contradiction is only, firstly, it's only possible with a with an unhomogeneous system of linear equations. So this would require at least so that we would have to have a b vector with some numbers, whatever, and these numbers would decide whether the contradiction comes along or whether it doesn't. Okay, so this has nothing to do with the coefficient matrix itself. Here, the determinant just decides whether a unique solution does exist or does not. In the end, if it does not exist, a contradiction depends on the numbers which you have here. If these are zeros, if you are solving the, you know, the homogeneous system of linear equations, you never get a contradiction. You always have the trivial solution at least. Okay, so that's also interesting. Well, anyway, so this was an addition just now. And here I put this as a remark, you know, for all other values of A, that's important. This SLA must have a unique solution, because then the determinant is unequal to 0. That's sufficient for a correspond for a matrix to be invertible. And if it's invertible, it means that also any system of linear equations you can represent with it has a unique solution. Okay, now everything confirmed, which we found in exercise 3.1.2. But please, if you don't remember, look it up. I don't have the time now to do it. The second method is quite nice. It's called Sarro's scheme. You may know it. Of course, you know it, but the question is, do you use the same graphical scheme as I do? I don't know. What I do is I put the matrix here, and then I construct sort of a cyclic repetition, okay? Exactly speaking, I take the first column and repeat it here, and then the second column repeat it here. And now I build these 3 different products which count positive, and the other 3, let's say, diagonal products or parallel to the diagonal product, which count negative. That's an easy scheme. We do it like 1 times 2 times 2 equals 4. So next product is 2a positive, then 1a positive, and then the 3 negative ones are, let's take care here, 1 times 2 times 2. So this is 4, but it counts negative. I have a minus 4, and then a squared minus a squared, I should say. And then 1 times 1 times 2, this is 2, but it also counts with a minus. So let's see what we have. I can cross out 4 against minus 4. It remains minus a squared here, then 2a plus a is plus 3a, and then minus 2, and you see it's exactly the same polynomial as before. Fine, the same result. Third method, this is just an addition now, for short. You should remember, by the way, exactly from the same exercise here, 3.1.2, where we solved this, I think it was, yes, it was an inhomogeneous system of linear equations using exactly this matrix as a coefficient matrix. And you would have to remember now that what we did before we found was it before? Yeah, or right after, just before or right after finding the first special case, we had already achieved the upper triangular form, the echelon form. It looked exactly like this. And if you remember, I made a little like a cosmetic correction there, because it looked nicer to have the same factors all along instead of different ones. And that's why I multiplied this lower row by -1, by -1. This is the only step I made which has an influence on the value of the determinant. The other, you must look it up to understand what I'm saying. The other steps we performed were just, well, what we are doing most often, namely adding rows. That's it. And you can even, that's interesting, you can even add, for example, you take one row times 5 and add it to another row, and still it has no influence on the determinant of the resulting matrix. That's an interesting fact. And so because we just were adding rows, it never had any change, it never made any changes on the determinant. And this means we do not have to start out again. But one thing you would have to know, you do not need a diagonal matrix in order for the diagonal product to be exactly equal to the determinant. More easily speaking, it's sufficient to have upper or lower triangular form in order to calculate the determinant by just taking the main diagonal product. That's the important point. And if I do this here, I get 1 times 1 times this, which I had already put in this nice factorized form, which is a minus 1 multiplied by a minus 2. And now you see, because of this this additional step of factor -1, I have to put a minus before, and again we get exactly the same polynomial as before. So that's nice.